In this lecture, we'll talk about bits and bytes. So everything in a computer is stored in binary, and binary is just ones and zeros, because a computer's memory is a set of tiny transistors, think of them as switches, that can be on or off, and so they can either be 1 or 0. We can cover the bit and byte terminology immediately because a bit is a single 1 or 0, and a byte is 8 bits. So, you could reasonably ask, why do we care? And we care because anything that we store in a computer has to be represented in binary, so we have to have some understanding of how that works. But we also care because everything that we can imagine can be represented in ones and zeros, which makes computers very powerful. The next question, though, given that computers have a limited amount of memory, how many bits do we need to store a certain number of things? And that requires that I tell you a Christmas story. So one morning a few years ago, 4 of us in my family were trying to determine who was going to give the first present. That's a tradition in our family. And my son and I, my son is a computer scientist, as am I, came up with one solution to this problem. And my daughter and wife came up with another solution to this problem. So pause the video for a moment, and we wanted to figure this out by flipping a coin. That's an important piece of information because a coin, of course, can end up being a 1 or a 0 if you think of heads as 1, 0 as tails. So think of how you would solve this problem. Pause the video and think of how you would solve this problem with coin flips to pick one of the 4 people. Okay. One of the common solutions that we might use would be to have a tournament. This is sort of a standard structure that you see in, playoffs in hockey or some other inferior sport to hockey. So you have these ladders, if you will, and you have A plays B and somebody wins, and that would be one coin flip. C plays D and somebody wins, and that would be another coin flip. And finally, the winner of those first 2 games, if you will, play with one more coin flip. So you can do that with 3 coin flips. And that's a very natural, normal way to come up with a solution to this problem. However, I'm going to be very dramatic here. We can use the power of binary. And we can actually encode A, B, C, and D, each of those 4 different things, by using 2 bits. And so if we encode A as 0, 0 and B as 0, 1 and so on, we can actually determine who wins with only 2 coin flips. Now, I will freely admit to you that we spent far more time talking about why this is a more efficient way to do it than it would have taken to just do a 3rd coin flip, but that's how my family works. So we actually discussed how this actually works. The second important idea behind this lecture is that we can encode things with binary using a certain number of bits. And figuring out how many bits we need to do that is a straightforward mathematical thing. If we have 1 bit, we can encode 2 different things, 0 and 1. If we have 2 bits, we can encode or represent 4 different things, 0, 0, 0, 1, 1, 0, and 1, 1. And yes, for the really geeky people, I've got to tell you, I was counting up in binary because, let me fix my glasses, that's the way I am. There's a general mathematical equation that tells us if we have B bits, how many things can we represent? And that equation is 2 raised to the power of B equal n. And here's a slide with the biggest font you'll see throughout this course to capture that information for you. So all we have to do is take B, raise 2 to the power of B, and that tells us how many things we can represent. Of course, if we know how many things we need to represent, we can calculate our B by taking the log base 2 of n. So, of course, we can use the inverse mathematical relationship as well to find B if we know n, but we'll usually just talk about 2 to the B equal n. And that's it for this lecture. The core ideas are we can represent anything in the computer using binary, using 1s and 0s, and we can calculate how many different things we can represent given a certain number of bits by using 2 to the b equal n.